Okay, so good evening, everyone, and welcome to uh, this edition of the Vigyan Adda, one of ICTS activities. Some of you perhaps are joining this for the first time. In fact, this is only our second Vigyan Adda program that we are having. The first one was held about a month ago by Professor Subrat Raju from ICTS. And we are very happy this time to have another of our brilliant faculty, Professor Parameswaran Ajith, to be telling us about an exciting topic at the forefront of current day research on gravitational waves and what the information one can learn about the universe specifically through gravitational lensing, the topic of this talk. Let me say a few words about the Vigyan Adda itself. This is an online activity, of course, due to circumstances, but we also hope that even after, once things are better, we will continue this online as a way of engaging with the large number of young people interested in science and scientific research. ICTS has other number of activities like the Copy with Curiosity, which is now called Curiosity During Quarantine, which is usually held in person at the planetarium in Bangalore. Though this has migrated online, but once things are better, that will go back to the in-person format. But Vigyan Adda is something we would like to keep in this online avatar, and the idea is to very directly reach a large number of participants from all over the country and indeed all over the globe. I already see in the chat message someone has joined from South Africa. So this is the idea behind the Vigyan Adda. It's also a little more directed towards young students and people who are potentially thinking of science as a career, to make them aware of some of the exciting new areas of research. So unlike Copy with Curiosity, which is a lot more broad-based and in fact touches upon several topics and caters to a very wide audience, scientifically interested members of the public and so on. This too is of course open to everyone, but with a slight slant towards people who might be considering going into science, and to create that awareness about exciting science being done in India as well. And so many of the speakers in this will be from Indian institutions, and we have started with ICTS. ICTS itself is a new institute, part of the Tata Institute of Fundamental Research, and with its core mandate to not only carry out frontline research, but also to organize programs and workshops, bringing researchers from around the world to India, to our campus, and train younger researchers, PhD students and postdoctoral researchers, by giving them exposure to the best science in the world. And our programs are organized by scientists from around the world who come to ICTS. They put together a proposal to organize a program, and then once that is approved, this is organized at ICTS. You can see all our talks on our YouTube channel or on our ICTS webpage. So the talks, both the technical ones of our programs, have a lot of valuable pedagogical material for those who might be seeking to learn about a new area like gravitational lensing, for instance. So supposing you're more interested after this talk to learn go into more details, Ajith and his friends have been organizing gravitational wave astronomy schools at ICTS for the last several years, and with many detailed talks on topics such as gravitational lensing. So you will be able to go and listen to those lectures. Similarly, all our outreach activities are also archived on the YouTube channel. It's called ICTS Talks, by the way, without any space, all small letters. You can link to it from our main webpage. So this is very briefly about ICTS. And let me now just quickly introduce the speaker. So it's really nice that Ajith volunteered to give this Vigyan Adda session. And Ajith is one of the faculty members at ICTS who is heading our astrophysical relativity group, and he has been he's a leader in the subject of gravitational wave physics. He did his PhD at the Max Planck Institute for gravitation in Germany, and afterwards was spent time at Caltech, and came back to India now over 7 years ago, and been at ICTS, where he has, as I said, built up a wonderful group involved in the LIGO scientific collaboration. It was ICTS's great pride that 7 members of ICTS, Ajith, as well as several others, including some of his students and postdocs, were members of the LIGO scientific collaboration at the time that the epochal discovery of the gravitational waves were made in 2015, announced in 2016. So that was a feather in the cap of not only Ajith and his group, but all of ICTS took pride in this achievement. Ajith has been recognized for his stellar work by several awards and fellowships. He is a Ramanujan Fellow. He received one of the few Canadian Institute for Advanced Research as really global scholarships, and he heads the Max Planck Partner Group at ICTS on astrophysical relativity as part of the LIGO scientific collaboration. He and his team members were part of the recipients of the 2016 Special Breakthrough Prize in Fundamental Physics and the 2016 Gruber Cosmology Prize. And very recently, we were thrilled when Ajith was honored with the inaugural World Academy of Sciences Young Scientist Award for Frontier Science. And this, again, is a very fitting recognition for his work. So you're in for a treat with Ajith communicates very passionately and lucidly with members outside the research community as well. So I invite you to listen to this talk, and those who have missed it, you can point them to the YouTube link afterwards. But let me hand it over now to Ajith.
Thank you, Rajesh, for the very kind words. And good afternoon. And I'm very grateful to all of you for joining us on this Sunday afternoon or morning or late night, wherever you are. I thought I would give you a very short history of this exciting topic of gravitational lensing, which was one of the most important observational evidence that verified the that verified the Einstein's theory of gravity, called the general theory of relativity, and it sort of heralded the remarkable success of Einstein's theory over the next century, which we all celebrated last year. It's 100th anniversary of the very first observation of the gravitational bending of light by Eddington and colleagues. So I will start from this very beginning to give you a flavor of the history. And the first half of my talk, I would talk about the gravitational lensing of light, which has a long history, about 100 years. And in the next half, I will talk about the gravitational lensing of gravitational waves, which has no history, but I think it has a very bright future, or a very loud future, if you use the word of vocabulary of gravitational waves. So let me start. I guess all of you know that the theory of general relativity, which was put forward by Albert Einstein in 1915, is the most accurate theory of gravity that we have right now. And this is the theory that predicted a number of very interesting observable phenomena, including gravitational lensing, gravitational waves, existence of black holes, expanding universe, and things like gravitational time dilation, and all kinds of things. And all these theoretical predictions have been verified by a number of very remarkable experimental tests, as well as astronomical observations. And so this theory is a very dramatic departure from the earlier theory of gravity that existed until now, just due to Newton. According to Einstein's theory, gravity is a manifestation of the curvature of space-time. So any massive objects or other forms of energy, like electromagnetic energy, would curve the space and time around it. In fact, we also learned from Einstein's earlier theory of relativity, which is a special theory of relativity, that the space and time are not independent entities, but they are all part of a single entity called the space-time. And in the absence of gravity, or any massive objects or other forms of energy, the space-time is completely flat, and the geometry is described by a simple extension of the Euclidean geometry that we all learn in school. But for example, in the presence of a massive object, in the vicinity of a massive object, this geometry of Euclid ceases to be valid. And one has to use an extension or a generalization of those calculations, which was due to Riemann, etc. So if you think of in physical terms, very, very far away from massive objects, or in the absence of gravity, space-time is completely flat. So one could actually verify its flatness by, for example, drawing a triangle and adding the angles inside the triangle, and you will get 180 degrees. But if you repeat the same exercise in the vicinity of a massive object, and if you have a precise enough measurements, and if you add the angles inside a triangle, they won't add up to 180 degrees. So, although this is rather like a thought experiment, one could actually think of real physical manifestation of the curvature of space-time that manifest in various kinds of astronomical observations, as well as daily life. So one such remarkable observational prediction of Einstein's theory is that gravity bends light. So we know from our usual experience, day-to-day experience, that light travels through straight line. And that's because the shortest distance between 2 points in a flat space is a straight line. And when the space-time is curved in the presence of a massive object, the shortest distance between 2 points is not a straight line. The generalization of that is called a geodesics. Mathematicians call it geodesics. And light basically travels through geodesics of that space-time. And if, for example, this is my cartoon of the space-time curved by the sun, And if there is a distant star whose rays are grazing the limb of the sun, in the vicinity of the sun's gravitational field or curved space-time, light travels to the geodesics of this curved space-time. So the observer who is looking from the other end would see a shift in the position of the star. So this, since we know the mass of the sun as well as the original location of the star, one could actually calculate the expected shift in the apparent position of the star when the star's rays are grazing the limb of the sun. And in the beginning of 20th century, 1919, during a total solar eclipse, a team of, in fact, two teams of astronomers led by Arthur Eddington, the British astronomer and physicist Arthur Eddington, set forward to observe the gravitational bending of light from distant star during this eclipse. So this eclipse was observable from mostly from the southern hemisphere. So they sent two teams, one to Africa in the island of Principe, which is in the west coast of Africa, and another team also went to Brazil also. So this is a location of the island Principe in the west coast of Africa. And in the middle, I show one of the actual photographic plates taken by Eddington's team during this eclipse. If you squint very, very carefully, you would see the stars, but it's rather hard to see that. So I have made a cartoon version of this. This is a cartoon version of what Eddington and his colleagues observed during this eclipse. So what they observed, during this eclipse, the sun was basically aligned with a cluster of stars called the Hyades cluster. It is in the constellation Taurus, the bull. And they observed basically the position of the star during the eclipse, which is shown by these red stars in this cartoon. And after a few months, they observed the same cluster of stars in the night sky, and the sun was not in between us and them. And that is like a reference location of these stars, which is shown by these blue stars here. And then you can very clearly see, if you align them, you could clearly see that the angular position of these stars have shifted during the eclipse. And according to Einstein's theory, this angle of angular shift can be calculated to be equal to 4gm by RC square, where g is the Newton's constant and c is the speed of light and m is the mass of the sun, and r is the location of the star measured from the center of the sun. And for example, if for a star whose rays are grazing the limb of the sun, this predicted angular shift is of the order of it's like 1.75 arc second. The Newtonian theory of gravity, one could also derive an angular shift like this, but the conceptual interpretation is a bit problematic. But even if you do this calculation, the predicted angular shift is only half of this. So the question was whether whether there was any shift in the angular position of stars during the eclipse, and if yes, whether it matches better with Einstein's theory or Newton's theory. And it turns out that these observations are consistent with Einstein's theory, which made a huge amount of news when Eddington and his colleagues announced the results of these observations in a Royal Society's meeting in November 1919. So this was reported all over the world, made Einstein a celebrity internationally almost overnight. For example, in the right side is a front page of the New York Times, and the headline says, "Lights all askew in the heavens, and Einstein's theory triumphs," etc. It also says like stars were not where they seem to be, but nobody needs to worry, etc. It made this news not only in the Western world. in the left-hand side is a article written by Meghnad Saha at the Calcutta newspaper, The Statesman, where Saha very emphatically states that if this Eddington's observation were to be proven right, then this would completely change our perception of space and time. And this Einstein's theory that predicts this completely revolutionize our understanding of space and time. And that is what happened in the last century. Now we know that our understanding of space and time has changed in a revolutionary manner due to this Einstein's theory. And now these gravitational bending of light is a very commonplace phenomenon in astronomy. In fact, there are very, very dramatic versions of this observation that astronomers routinely make, especially in the last few decades. And these are called gravitational lenses. Basically, very, very massive objects like galaxies or clusters of galaxies basically curve their space-time around them so strong that the light from distant stars and distant galaxies are focused by the presence of this gravitational lens. And we could see sort of even multiple images of the same source due to this lensing effect. So here is a cartoon version of this. We are on the bottom left corner, the Earth, and there is a distant galaxy at the top right corner. And in between us and this distant galaxy, there is another galaxy, which is very massive, and it curves the space-time around it. And light from this background galaxy can come towards us through multiple paths because of the curvature of space-time. And because the light gets focused at these multiple paths, we can get to see multiple images of the same source. This is like an extreme example of gravitational lensing, and there are gravitational lensing comes in many forms. For example, strong, weak, or micro, like good, bad, and ugly. So these are some real examples of how the gravitational lensing would appear in these circumstances. For example, in the leftmost plot is an actual image of a quasar, a very distant quasar, which is lensed by another galaxy or a cluster in between us and this distant quasar. And because of the geometry of the lens, it turns out that you form 4 images of this lens. So this is called strong lensing. So for example, if the projected mass density of the lens is greater than a certain critical density, it can produce multiple images. This lens can produce multiple images of the source. And the left-hand side shows such a quadruply lensed image of a distant quasar. I think this is an X-ray observation, if I'm not mistaken. And the middle plot is what is called an example of a weak lensing. Here, the projected mass density to our line of sight or to the plane perpendicular line of sight is not that large. It is less than a certain critical density. Then the lensing is not strong enough to produce multiple images. So what instead it does is to distort the shape of the background objects. And here you can see certain very characteristic arc shapes, which are basically usually looking spiral or elliptical galaxies in the background, distorted by the lensing potential of a foreground lens, which is getting a cluster of galaxies. And by studying the distortion of the lens, and if you assume certain statistical properties of the shape of the background galaxies, one could actually infer the mass potential, the potential or the mass distribution of the lens that is causing these distortions. So this is like analogous to the kind of ripple pattern that you would see in a swimming pool, So for example, if you have a swimming pool that has a very regular grids, and when the water is moving, water is making waves on the swimming pool, you would see that this background grid get distorted. And if you know exactly the geometry of this background grid, you can actually calculate the shape of the waves. In principle, if you know the refractive index of water, etc. Similarly, you can. This is the way we, astronomers sort of solve this inverse problem of computing the lensing potential from the distorted image of galaxies. In practice, you do not know the actual shape of background galaxies, but if you make some statistical assumptions that the shapes are, galaxies are isotropically distributed, there are no preferred directions, etc., one could statistically infer the presence of such weak lensing, which has become a really powerful tool to map out mass distributions in the universe, because the lensing does not care whether the mass is luminous or dark. So lensing has now become a very powerful tool to distribute, to map out the distributions of dark matter in the universe. Another very interesting example of lensing is the so-called micro lensing, where the lens mass is very, very small, so that the critical lens, it's much smaller. The density is also very, very small, so that it cannot produce any significant magnification in general, as well as multiple images, certainly. But if, for example, the lens somehow comes in front of a background source, then you would see a sudden increase in the magnification to the distant source. So one example is, for example, if you're looking at a distant star for a long time, and if some other object, like a star or a black hole or a planet or something like that, comes in between us and the distant star, then that microlensing effect of that lens would focus light from the distant star and would increase the observed flux for a part of the time during this transit. So you would see this characteristic pulse that is a telltale signature of the microlensing. And this is now a really powerful tool now to, for example, detect, for example, the presence of, for example, black holes or exoplanets, planets outside the solar system, etc. So in the last few decades, gravitational lensing has emerged to be a really powerful tool for astronomical and cosmological explorations. So I'm giving a few examples of the power of gravitational lensing. Gravitational lensing has been used to gather evidence of dark matter. So here is one very famous example in the top panel. So as I told earlier, by studying the weak lensing distortions of galaxies, one could actually map out the mass distribution of the lens that is causing these distortions. So here is the top left plot is such estimation of the mass distribution of a lensing cluster. This is called the so-called bullet cluster, and these green contours are where the masses are concentrated. The mass is concentrated in this cluster of galaxies. So where the contour lines are closer, the mass is the largest, as the usual interpretation of contour plots. But now, if you look at this cluster using X-rays, which is the right plot, it turns out that the luminous part of this cluster is not where the mass is concentrated. So the luminous part is shown by these yellow and white regions. And you can see a very visible offset between the luminous part of this cluster of galaxies and the massive part of this cluster of galaxies. So the conclusion is that most of the part of this cluster, most of the mass of the cluster is in the form of dark matter, which has an offset from where the luminous part is. But roughly, if you look at the very cosmological scale, cosmologists can see that by looking at much larger fields. These dark matter potentials essentially serve as sort of seeds or potential wells where the baryonic matter accumulates and eventually form galaxies and et cetera, et cetera. And similarly, doing this for a large number of galaxies, both strong lensing as well as weak lensing, one can map out such mass distribution of dark matter in the universe, and this is when some very strong observational evidence suggesting that a significant fraction of of the mass in the universe is in the form of dark matter. It has some diffuse sort of thermal distribution also. Also, interestingly, gravitational lensing once in a while can provide some very, very magnified images of distant galaxies and stars. So it's like having a magnifying glass to look at some objects. So you can see them much brighter and with much better magnification. So some of the very, very distant galaxies, which could not have been observed otherwise, are now we are able to observe them purely because of this magnification provided by gravitational lens. So you also know that distance in cosmology, astrophysics, means that these objects were also coming from earlier in the history of the universe. So these stars, or these galaxies and stars, are also the first or early galaxies and early stars in the cosmological history. So lensing, because of this extra magnification, provides us a way of studying the first stars and galaxies because of this extra magnification. There were some really extreme examples observed in the last few years. One is the observation of a star at a distance of about 9 billion light years, because it got magnified by some 2,000 times due to a cluster which happens to be in between the star and us. So it is very, very rare to see stars from such large cosmological distances, but lensing provides some ways of observing them. I told you that lensing provides a very, very neat way of identifying dark matter and to map out its distribution. But also lensing, microlensing, for example, is used to identify or constrain at least the nature of dark matter also. Just to take one step back, we know through a variety of astronomical and cosmological observations that about 25% of the total mass energy in the universe is in the form of what is called dark matter. We cannot see it, but we can see its influence, its gravitational influence on other luminous objects like motion of stars and etc. That's why we know the dark matter exists. But it is not entirely clear what is the constitution of dark matter. So one most popular belief is that dark matter is comprised of some particles, some fundamental particles, which are beyond the standard model of particle physics. And there are a number of such experiments going on to identify such dark matter particles colliding and probably producing some observational signatures. But none of them have found any evidence, any serious evidence so far. Another possibility is that the dark matter could be comprised of a large number of compact objects, like small black holes or planets or any object that doesn't emit light but has some mass and hence produce gravity. And if that is the case, these are called compact dark matter or machos. If that is the case, if you, for example, look at a distant, like in our neighboring galaxy, several stars in our neighboring galaxy, through the dark matter halo of our galaxy, because the dark matter is much more diffuse than ordinary baryonic matter and has a much larger spatial extent. And if you look at the neighboring galaxy through this dark matter halo, then you should see that once in a while, some of these compact objects would come in between us and stars in the neighboring galaxy and produce a microlensing effect, which is like a time-dependent increase in the magnification. So you could either detect the presence of such compact object, or the absence of such detection can put an upper limit on the fraction of dark matter that is contributed by these compact objects. So it's a powerful way of constraining this hypothesis that dark matter could be due to compact objects like primordial black holes and similar kinds of objects. The same principle can also be used to detect planets outside the solar system. Again, there is a very interesting telltale signature of planetary system. So the bottom right plot is a cartoon of an sort of extension of what I showed in the previous slide of a microlensing observation. So there is a yellow star at the top. It's a distant star, and there is another star that comes in between us, which is we are at the bottom, and the source, which is at the top. And you should see this increased magnification, increased flux due to the magnification caused by this transiting star, just this sort of pulse shape. But now if this star, this lens star, also has a planetary system around it, then this little planet should cause some additional lensing effect on top of the lensing effect caused by the star. So you would see on the right side, you would see an extra blip on top of this pulse that is contributed by the lensing of the star. So such lensing observation has been used to identify extrasolar planets, exoplanets, and dozens of such planets have been observed from the data of the Kepler satellite using microlensing observation. So there has been a number of such uses of gravitational lensing, and it has become one of the most powerful tools for astronomers and cosmologists in the last few decades. And let me switch gears now. So just like the gravitational bending of light was originally thought of as a way of testing Einstein's theory and has now become a powerful tool for astronomical exploration. A new tool for astronomical observation was available to us in the last 5 years to the detection of gravitational waves. And the existence of gravitational waves also was predicted by Einstein's theory of general relativity. And gravitational waves are wave-like solutions to Einstein's equations, mathematically speaking, and they can be thought of as oscillations or disturbances that are propagating on the geometry of space-time. So any massive object that moves with an acceleration would produce these ripples in space-time, and as they propagate and reach us, they change the geometry of the space-time that we live in. They produce distortions in our space-time, which can be measured using very precise detectors, which are called laser interferometers. And in the last 5 years, the LIGO observatories, as well as its sister observatory called Virgo, have observed dozens of such gravitational wave signals coming from colliding black holes and colliding neutron stars at different parts of the universe. And we are basically, with these observations, we are opening up a new branch of observational astronomy. So here, for example, is a catalog of the gravitational wave sources that we have detected in the last 5 years. So the vertical axis is the mass of these compact objects in binary systems. These are gravitational waves are produced by motions of two compact objects, which could be black holes or neutron stars in a binary system. So they move at very, very fast velocities, comparable to the speed of light eventually. And these disturbances produce oscillations in space-time, which propagate outwards. And they take away energy from this orbit. And as a result, the orbit comes closer and closer. So these objects spiral inwards, eventually merging with each other, producing a more massive compact object, which is most of the time a black hole, which is rapidly spinning also. So these vertical axis shows the mass of these compact objects in the binary system in units of solar masses. So one is the mass of the sun, and 160 is 160 times the mass of the sun. So each of these mergers basically involves three objects. You start with two objects, two black holes or two neutron stars orbit around, and finally they merge to form a much more massive object, which is mostly a black hole. So you can see this, each cluster connects two dots to one more massive dot. And these blue dots are the black holes discovered by LIGO and Virgo. And if you compare them against the black hole candidates discovered by X-ray observations from our own galaxy, and these are from what is called X-ray binaries, where one star is orbiting a black hole, and by studying the emission of the accreting gas from the star, X-ray astronomers can measure the mass of the black holes. And it turns out that the mass of the LIGO black holes are typically the LIGO black holes are much more massive than the black holes in our own galaxy. So this is a surprise to most astronomers that there are these new populations of heavy black hole that exist in the universe. Similarly, we also have a few observations of merging neutron stars, and there are some one mystery object also, which is not one object it is not clear whether it is a black hole or a neutron star. It could either be the most massive neutron star observed or the least massive black hole observed. So, and we have currently no way of telling between them. In either way, it's a surprise object. And so these observations are really opening up a new way of observing the universe. And as we speak, we have more data coming up, being analyzed, and we expect to see many more signals in the next few months. So these observations have produced some very, very interesting science. So, for example, these are the first observations of merging binary black holes. As I mentioned, they provided the evidence of stellar mass black holes, which are much more massive than the kind of black hole that we have seen before, more than 30 solar masses. There are some potential evidence of what is called the intermediate mass black holes, which are black holes more massive than about 100 solar masses, but less massive than about 10,000 solar masses or so. And these LIGO and Virgo made a very remarkable observation of a merger of two neutron stars. And we not only observed the gravitational waves from them, we also observed the electromagnetic counterparts of this merger through a variety of astronomical observations, electromagnetic telescopes, starting from gamma rays and all the way up to radio. And there are many, many additional event candidates coming up. And in particular, this very exciting and mysterious object, which is from this binary GW190814, which is named after the date of its observation. It is either the lightest black hole ever observed or the heaviest neutron star ever observed. So I encourage you to read these very accessible science summaries of all the LIGO Virgo papers, which are accessible from the LIGO Virgo webpage, and apart from the actual publications in the LIGO Virgo scientific collaboration. And it is important for us to remind ourselves that the gravitational wave astronomy has only begun. We're just beginning the first steps of this new branch of astronomy. These observatories like LIGO and Virgo have not yet reached their design sensitivities. And each small improvement in their sensitivity will actually gain us a significant increase in the event rate, in the volume of universe that we are able to observe, and hence the event rate. And if you just extrapolate the projected increase in the sensitivity of these observations and our understanding of the rate of such merger events happening in the universe, in the local universe, we can safely predict that in the next few years, we will be observing several hundreds of compact binary mergers using LIGO and Virgo. And this could even lead to several thousand. And this would provide a number of very, very interesting probes of fundamental physics, astrophysics, and cosmology. I don't want to go to the details, but there are some very, very interesting questions that are that modern astronomers and cosmologists and fundamental physics ask. And gravitational observations could provide some very interesting constraints, or in the best case, some answers to these puzzles. And from an observational point of view, one very interesting thing that we from the Indian community are excited about is the ongoing program to build a LIGO observatory in India called the LIGO India, which has a target operation of beyond 2026 or so. And this would enable us to be part of a major frontier of science in the next decade. So one such frontier, in my personal opinion at least, is the gravitational lensing of gravitational waves. So it turns out that according to Einstein's theory, gravitational waves are bent or lensed exactly in the same way as electromagnetic waves. And if you fold in our expected detection rates and our sensitivities and the distribution of lenses in the universe, such as galaxies and galaxy clusters, it turns out that a small fraction of the gravitational waves that we observe in the next several years would be lensed by intervening galaxies and sometimes clusters also. It's a small fraction. That fraction is of the order of 0.1% to 0.5%. But because we are expecting several hundreds and possibly several thousands of events in the next few years, we expect by pure statistics that a few of such events would be gravitationally lensed by intervening matter, like clusters or galaxies. So this is very interesting, and just like we have seen these multiple images of quasars, etc. We will also see multiple images of these gravitational wave events. So here is a right-hand side is a cartoon. So there is a merge that is happening at a distant galaxy, and on the other side is the LIGO Virgo detectors, and there is a galaxy in between us and the source. And because of the curvature of the space-time, there are multiple paths, multiple geodesics connecting us and the source, and then that's how we get these multiple images. And unfortunately, the image separation of the angular separation of multiple images, which is of the order of gm by c square r we discussed, is of the order of arc seconds. And this kind of resolution is resolvable using electromagnetic telescopes. But unfortunately, gravitational wave observatories have very poor angular resolution. So these angular separation is not something that these gravitational observatories can resolve. But they can resolve some very interesting other things. You can resolve them temporarily, because these merger events are transient signals. They last only for a fraction of a second to a few seconds in the frequency band of gravitational wave observatories. And these lensing produces a time delay between multiple images or multiple paths. And these time delays could be anywhere between minutes to hours, or sometimes even weeks also. So what you should see is, once gravitational wave signal would arrive first, and after several minutes or several days or several weeks, a copy of the same gravitational wave signal would arrive second. This is something rather difficult to observe in electromagnetic observations. Although there are similar examples of that been observed so far, like an exploding supernova has been observed in a lensed image. So 100 years after Eddington's observation of the bending of light, we are in the verge of detecting the gravitational bending of gravitational waves. And this can have some very interesting implications. So just like the magnification produced onto light, gravitational waves also magnified in the same way. So for example, the polarization, so most of the dominant contribution to the lens is from the galaxies, and here because of the mass or the gravitational length scale of the lens is so large as compared to the wavelength of gravitational waves, you can treat them in pure geometric optics or ray optics calculations. And the only effect on this lens is a magnification. So it doesn't, for example, affect the shape of the signal. So here's some cartoon example of two sort of copies of gravitational waves, the relative magnification. So you can see that the second image is a demagnified version of the first image. And that magnification factor is given by the square root of mu. And once in a while, you can get some really high magnification in the lensed images, which should act as some kind of cosmic magnifying glasses, which should allow you to see very, very distant sources which would not have been observable otherwise. So here is an actual left-hand side is an actual example of such an highly magnified image of a star using electromagnetic observations to optical observations. So there is the left pole plot is a cluster of galaxies which is acting as a lens, and in the right-hand side there is in the bottom right there is a little dot at the tip of the arrow, which is a star. It's a star that 9 billion light years, which is a hopelessly distant star in usual standards of astronomy. So for example, if astronomers looked at the same patch in 2011, they could not see any trace of the star. But after 5 years, because of the relative motion between the star and this cluster lens, there was a cosmic alignment, and that magnified the star, which made it visible in 2016. So similar, the same thing can happen in gravitational waves also. So we have not observed it yet, but using theoretical calculations, we could actually predict how far you can see because of this lensing effect. So here is, on the right-hand side, is as an estimation. So typically, the gravitational observatories have some horizon beyond which we cannot see gravitational wave sources. And that horizon is depending on the mass of the source of gravitational waves, the black hole binaries, for example, because the more massive a binary, the louder is the gravitational wave signal. So that's why typically you have, so this green plot here is the horizon distance as a function of the total mass of the binary black hole system for, say, advanced LIGO detector. And so all these binaries sort of before, or with redshifts less than, or distances less than this horizon distance, will be observed using LIGO, and nothing outside, nothing above this horizon distance will be visible. But because of the lensing magnification, you can see a fraction of these events outside this horizon distance also, and that is shown by these yellow regions. So here, these color contours shows the number of events detectable by LIGO. Red means larger, yellow is intermediate, and blue is sort of 0. So this extra region, yellow region above the green line, is this new population of sources that has contributed to our observational sample by lensing. And this could also, in the case of these stars, one could actually accurately estimate the distance to the source because of the spectral signatures of various lines in the stars. So one could do a spectroscopic measurement, and that would give us the cosmological redshift. But unfortunately, in the case of gravitational waves, there are no such spectral lines, and there are no characteristic frequencies also. I mean, all frequencies are scalable with mass. So our measurement of distance is based on some kind of a standard candle. So we can measure the mass of the system from its frequency evolution of the signal. And if you know the mass of the signal, we can calculate its absolute brightness or absolute amplitude. And since we measure the apparent amplitude or the apparent brightness, they are related by the luminosity distance or the square of luminosity distance in the case of flux. That's how we are estimating the distance. But now if the lensing basically magnifies a star or a binary black hole, it basically appears to be brighter. So it appears to be closer to us. So we would have a biased estimation of the distance to this black hole system. And it also turns out that this would also affect our estimation of the true intrinsic mass of the system. And it is another correlation because the gravitational redshift and the mass is correlated. If you have any, I'm not going to describe this now, but we can come back to the question and answer session. So to summary, this lensing would enable us to see such distant object, but we would have a biased estimates of their distance. We would estimate them to be closer, and we would also estimate their masses to be larger. So we would have a biased estimation of the mass of these black holes. And some authors also, in fact, argued that these massive black holes that LIGO have seen are a bias caused by the gravitational lensing. I told you that this massive black hole that LIGO have seen was a surprise to most astronomers. But the near consensus in the broad community is that this is a very stretched argument, because if you want this to be true, this claim to be true, one has to fine-tune a lot of things, the star formation models and binary black hole distributions, and the mass functions of black holes, etc. I mean, and you have to have really contrived situations to explain this through this lensing explanation. While nothing is stopping us from using a simpler explanation, that is that the true mass function of black holes include binary black holes with larger masses also. And also, if these lensing events were so common, you should have seen other telltale signatures of the lensing, such as the multiple events, etc. Anyway, there are some interesting arguments going on, and for example, this Scientific American article has some interesting popular summary of what is going on in this field. So that's why I'm coming back to the multiple images, because that is a real telltale signature of gravitational lensing. But while this is actually quite easy to detect multiply lensed images of distant sources using optical observations or radio observations or X-ray observations these days, because these observatories are so sophisticated now that the signal-to-noise ratio of these observations are millions or tens of thousands. And while in the case of gravitational wave astronomy, we are in the infant stages, so the signal-to-noise ratio of our observations is of the order of 10 or 20. So it's very difficult to identify multiple images or multiply imaged copies of the gravitational waves. The problem is to identify a handful of lensed gravitational waves among hundreds or thousands of unrelated binary black hole merger events in let's say a year worth of LIGO data. And that's like a needle in haystack problem. But the clue is to look for signals that are similar in shape. So this is sort of similar to the spectroscopy, right? The way to identify, to establish that two images are the lensed images of the same galaxy. What one would do is to compare their spectra. So in a similar way, gravitational wave observatories data also, you can look for signals that are of similar shape and are coming from the same location in the sky. And also the time delay between these multiple copies should be consistent with the time delays that we expect from the known distribution of lenses, because we know the distribution of galaxies in the nearby universe, and we can predict the distribution of time delays between multiple images. But the whole enterprise is challenging because of the low signal-to-noise ratio. So at our group, we developed a Bayesian model selection method that basically formulates this problem in a more rigorous way. So what we do, for example, is to, from any pair of gravitational wave signals, you have two hypotheses. One is that they are the lensed copies of the same merger, and another hypothesis that they are just completely independent binary black hole mergers. So from the data from these two events, you can calculate the odds ratio between the two hypotheses. And it turns out that this odds ratio is the inner product of the posterior distributions of the binaries parameters, source parameters that we extract from the data. And posterior distributions are some kind of a conditional distribution of the source parameters, like their masses, their spin angular momenta, etc., of the binary black holes, given the data. And if these signals are copies of the same signal, then intuitively we expect that they should correspond to same binary black hole masses, same location in the sky, etc. So we could more rigorously formulate this and write it in terms of a Bayes odds ratio. And similarly, we can also use our understanding of the distribution, the expected distribution of the time delay between events, because given a distribution of lenses and a given distribution of black holes, binary black holes in the universe, we can do an astrophysical simulation and predict the distribution of the time delay between multiple images. And here is an example of this calculated time delay. And if they are lensed, for example, which is a red distribution or the blue dash distribution, the CN dash distribution, they typically have time delays of the order of an hour or a few hundred hours. While if you look at a population of unrelated events, they would just follow some Poisson statistic, and then the distribution would peak towards thousands of hours or tens of thousands of hours. So that would give us a way of distinguishing between these true lensed events and unlensed events. So using these tools in hand, we in fact searched for evidence of lensing signatures in the LIGO Virgo data so far during the first two runs. And the conclusion is that so far we find no evidence of gravitational lensing in the in the first in the data in the events observed during the first 2 observing runs of LIGO and Virgo. So this plot is some way of assessing the significance of pairs of events. Since there are about 10 pairs, there are 10 events for binary black hole. There are 45 pairs, and these plot shows the evidence towards lensing. So there are 2 measures of the evidence towards lensing. One is based on how consistent they are in terms of their signal shape, which is the y-axis, and the horizontal axis is how consistent these 2 are to the lensing based on their time delay distribution, the observed time delay between 2 events. So most pairs, and each red dot here is a pair of events. For example, 170104 and 170814 means the gravitational wave signals observed during those days. And it only shows this most loudest events. Most events are very, very small, such likelihood ratio. So to summarize, currently there is no significance. This is significant evidence that suggests that any of the pairs of events are lensed. One could also ask how likely, assuming a population model of binary black holes, which suggests which involves some assumed mass distribution and assumed distribution in the cosmological redshift, how likely are the observed events to be lensed or not? The details are a bit involved, but again, to summarize, our conclusion is that one does not need to invoke lensing to explain the mass and redshift distribution of the observed events. One can explain them using simpler explanations. So, and because this lensing would be a remarkable discovery and an exceptional discovery, we will need an exceptional evidence, which we do not have to claim for lensing. So currently, we do not see any exceptional evidence of lensing yet. So these sort of things were similar to the lensing signatures in the electromagnetic waves. But gravitational wave observations, possibly for the first time, would also enable to see something that we have not seen before, which are wave optics phenomena due to lensing. So, for example, when the wavelength of the light or gravitational waves becomes comparable to the gravitational length scale of the lensing object, then interesting wave optics phenomena can happen, like diffraction and interference. This is similar to the diffraction of 2 light beams coming from like a double slit. So you slit width comparable to the wavelength of light to see some interesting diffraction pattern. So similarly, if the gravitational radius or the gravitational length scale of the lens is comparable to the wavelength of gravitational waves, which is of the order of 100 to 1,000 years, then one could see some interesting wave optics effects. And this would deform the observed signals, and one can calculate its deformation, and one can look for such signatures in the observed signal. So here is again a cartoon version. This gray background chirping signal is an unlensed image, and the red and black shows how these waveform would be deformed due to the wave optics lensing by a point mass object, which is about 100 solar mass, which is the red one, and 1,000 solar mass. So you could see some very interesting beating patterns. And it is easy to model these and one has to introduce parameters like the lens mass and some impact parameter, etc. And one can look for the evidence of such deformations in the observed signal. And again, we did a search for such evidence of lensing signatures in the observed signals, and so far we do not see any overwhelming evidence of lensing signatures in these observed events in LIGO and Virgo. But as I told earlier, because of the sheer number of events that we are expecting in the next few years, we are fairly confident that we will make the first observation of lensed gravitational waves in the next few years. So why is it a big deal? One would imagine that just like the lensing observations of electromagnetic waves have emerged to be a powerful tool for astronomical and cosmological exploration, gravitational lensing observations of gravitational waves will also evolve in such a way in the next decades. And we are only starting to think about what are the potential interesting applications of its lensing of gravitational waves. And we already have some very interesting ideas. One is that the multiple imaged gravitational wave lensed events would enable a precise localization of the merger event. And this is something very difficult to do using purely gravitational waves. And for example, if you compare, these are some of the reconstructed locations of the gravitational wave signal that we can reconstruct now. And they span several hundred square degrees in the sky. Even in the best case with LIGO India and like a 5 detector network, our ability to localize a gravitational wave signal in the sky is of the order of a square degree or a few square degrees. And even in this 1 square degree, there are millions of galaxies in the sky. And it turns out that if you have quadruply imaged gravitational signals, using the time delay and magnification ratio between them and combining them with some optical observations of host galaxies, one can actually spot the host galaxy of this gravitational wave event, which is a remarkable thing, because currently, although we are observing these hundreds of or tens of gravitational wave events from binary black holes, we do not exactly know how nature produces them. And the understanding the host galaxy and the host environment of its binary black holes would be a very key ingredient in our understanding of this astrophysical processes. One can also do some very interesting tests of fundamental physics using lensed gravitational waves. This is a work done by ICTS graduate student Srishti Goyal. And here the idea is that if you have, let's say, 2 copies of the same gravitational wave signal, you're basically observing the same event with twice the number of detectors. And the key aspect is that according to Einstein's theory, gravitational waves have 2 polarizations. And one interferometric detector basically measures one linear combination of the 2 polarization. And if you now measure 2 copies of the same signal with a time delay of, let's say, a few hours, then the detector would have rotated because of the rotation of the Earth. And in the second image, you would be observing a different linear combination of the same polarizations. So you have 2 equations to solve now, and you can uniquely solve for these 2 polarizations. And so basically, it is like doubling the number of detectors to observe the same source. So if you have a lensed event that produces multiple images, you're basically doubling the number of detectors in the international network of gravitational detectors. And this would significantly improve our ability to understand the polarization content of gravitational waves. And sometimes you can also ask whether this polarization content is consistent with Einstein's theory, because there are other theories of gravity that predicts extra polarization modes. Similarly, the wave optics effects that we can observe in the gravitational waves can also be used to constrain the fraction of compact objects that form dark matter, similar to what electromagnetic observations were able to do. But here, even a non-observation can be very useful, because, as I said earlier, if you stare at a lot of cosmos and you do see no microlensing effects or wave optics effects in any of these hundreds of signals, that you can use to put an upper limit on the abundance of compact object in between us and the source. And that basically can be used to constrain the fraction of dark matter in the form of such compact objects. And it turns out that, so this possibility has been heavily constrained in different mass ranges of such compact objects. But it turns out that LIGO is uniquely posed to put constraints in a region of mass space in the form of these compact objects, which is not heavily constrained by other observations. So LIGO is able to put constraints on the fraction of compact objects forming dark matter in the mass range of about 10 solar masses to a few thousand solar masses. So let me stop here, and I would like you to take some points home. One is that the gravitational lensing observations began as a way of testing the validity of Einstein's theory. That was the motivation of Eddington and his colleagues. But eventually, it became a powerful tool for the probe of astrophysics and cosmology. Similarly, gravitational waves also. And now it is becoming a really unique branch of observational astronomy, bringing up a wealth of information. The first observation of gravitational lensing of gravitational waves is expected in the next few years. So it was doubly Einstein. The gravitational waves themselves are a phenomenon predicted by Einstein theory of relativity, and now we are going to see a next sort of effect of lensing on top of these gravitational waves. And one would hope that this would be a very, very powerful tool for astronomers and cosmologists in the coming decades. And there are already indications of the same. So let me stop here, and thank you very much.
Thank you, Professor Ajith, for the talk. It was a wonderful talk. So I'll just quickly go to the questions now.
Sure.
You can have some water.
Yes, thank you.
So just at the outset, I would say that there are more than 25 questions. We'll just go through it as per the time permits. Okay. So the first question is by Weber Basin. He is asking, can gravitational lensing be created in lab?
In principle, yes, right? Because any massive object would curve the space-time around it. But the question is whether that effect is observable. And the answer is no conceivable technology can measure the gravitational lensing effects produced by objects in the lab.
Thank you. Next question is by Kartika. She's asking, can you briefly describe how can we probe dark matter using weak lensing data?
So I sort of gave a qualitative argument. So basically, what you hear is, if you, for example, know precisely what is the background image looks like, and then you have a lens that is distorting that image. And by sort of solving so for example, then you can do the forward problem, right? Given an image, you can calculate its distortion produced by any lens through the lens equation. So now you have this distorted image, and then you can solve the inverse problem if you knew the original image. So you can basically calculate the geometry of the lens if you know the original image and the distorted image. But in practice, you do not know the original image in the case of galaxies. But one can make a qualitative, sort of a statistical argument, because there is no preferred direction in space. So the orientation of galaxies in all directions should be random. So then one could make a statistical detection of the weak lensing because of some preferred directions in the distorted image.
Thank you, Professor Ajith. The next question is actually linked to this question, but still I'll ask if you have any further comments. Can our theoretical models be used to reverse engineer the path of light so that we can use ray tracing to map objects which are when they are distorted by lensing effect? This question is by Desmond.
Yeah, precisely. This is exactly what I meant. Maybe it was not clear, sorry. To calculate the distortion of the rays, one has to use a lens model, which depends on the mass distribution of the lens. And in general, it can be very complicated. So that's why you create a lens model, and then you apply it on a background image, and you can calculate distortion. And this way, you can inverse map a distorted image to calculate the lens model also. Or if you have a lens model, you can calculate the distorted original image, undistorted image.
Thank you, Professor Ajith. So next question is by Mintu. He's asking, light from any constellation may pass through the gravitational field, and then their location will change. So how can we calculate the perfect position of a star by using gravitational lensing?
Well, it's very rare. You didn't tell what gravitational field, because there has to be an object that is producing gravitational field, right? And it is very rare that another object would come in between a star and us. The probability is of the order of 1 in 1,000. So that is why the lensing is a fairly rare phenomenon. And that's why in a total sample, the lensed images are like a very small subset. So it doesn't really affect your statistics of the original location of stars, etc., in a large way. Especially stars are the stars that we can observe are very close, so the probability of seeing having a galaxy in between us and the stars is really, really small. So lensing is mostly important for very, very distant objects like galaxies and clusters and quasars, etc.
Thank you. Sushmita is asking, what is causing the flux increase when the star is in between in weak lensing?
In micro lensing, I mean, you mean, I guess. It is because the star's space-time curvature is focusing light from the background star. And that focused light is increasing the flux. That is the magnification, just like your normal lens would focus light.
Thank you. Next question is by Yogesh. Does curvature of space-time due to gravity effect of an object, say M, always remain the same, that is independent of density of the universe? Yeah, did you get the question, Professor Ajith?
I mean, the density of the universe is contributed by its constituent objects, right? So if you're thinking about the density due to the background vacuum energy, that is very small if in a gravitationally bound system. So in the presence of any massive objects of reasonable size, the density is dominated by that object, like a star or a galaxy, etc. And there, the lensing effect is dominated by the, let's say, dark matter halo of that galaxy or the total mass of the galaxy, etc. So I'm not sure the background, the average density of the universe plays any significant role there.
Thank you, Professor Ajith.
Of course, the whole thing is calculated in the background cosmology of the universe. It's called the Robertson, Walker, Freeman metric.
Okay. So I'll move on to the next question, Professor Ajith.
Yeah.
Yeah. Okay. So Anjita is asking, what exactly is the weak lensing data? And the next sentence is not very clear, but is it ellipticity of the sources or shear? I'll just come. Yeah, I'll complete the question, Professor Ajith. So can you suggest any statistical tool to probe the lensing data? This is the question.
Yeah, it is the shear. So basically, the shear of the background image is what is used as the signature of lensing. I am not an expert on the weak lensing analysis, but there are many tools that look for shears, like for some kind of curl features in the images, etc.
Thank you. Next question is by Vivek. Professor Ajith, thank you for the talk. He says, and how can we formulate the gravitational lensing which occurs with gravitational waves? Does it occur with gravitational waves and other ends of EM spectrum? I think it's a general question.
I didn't quite understand the question. Can you repeat the question?
I'll repeat the exact words. How can we formulate the gravitational lensing which occurs with gravitational waves? Does it occur with gravitational waves and other ends of EM spectrum?
Okay, I guess your question is how do you formulate the lensing of gravitational waves? It is the similar way as the formulation of the lensing of electromagnetic waves, except that gravitational waves are different from electromagnetic waves. While so one has to use that calculation. So while electromagnetic waves are a vector field, gravitational waves are a propagation of tensor fields. So, but it is all done in the framework of GR.
Thank you, Professor. I'll move on to the next question. Next question by Peter. Are there already discovered signs of temporal lensing effects in the observed LSC data?
Not in the gravitational wave data, but there are temporal lensing effects discovered in the electromagnetic observations now. One is the observation of a gravitationally lensed supernova. So astronomers first discovered a supernova first, and then predicted that it would. There was a cluster in between the supernova and us, and they predicted that the second image would arise after a year or so, and then they did see that. But no lensing effect have been observed in gravitational waves yet.
Thank you, Professor. This is a very different question, but I'll still ask how well Vedic mathematics can be helpful in understanding cosmic phenomena. This is by Santosh. Yeah.
So I am also, there are many mathematicians have studied it very carefully. I think what, one has to be careful in defining what Vedic mathematics is. There are some very, very important contributions to mathematics in India, which are widely acknowledged, and there are professional historians and professional mathematicians studying it very seriously, and including some very interesting contributions to calculus, etc., which was not Vedic, which is only a few centuries ago. But what is commonly presented as Vedic mathematics is some kind of some tricks or doing algebra, etc., which my understanding, it has nothing to do with Vedas. This text is only a few tens of years old, in some 70 years old, etc. And this is some, in terms of actual serious mathematics, this is not something very rigorous, and it's some tricks to do some calculations. And I don't think that such tricks have any significant role to play in scientific research. So there are people like a mathematician, Professor Dani from TIFR, studied and very carefully and written about it. And there are several other mathematicians and historians of science have written very seriously about contributions to Indian mathematics. So if you are actually seriously interested in the Indian contributions of mathematics, I would encourage you to read those books.
Thank you, Professor Ajith. Since this talk is targeted to UG students, a question from Ashwin George is, for a student doing bachelor's in physics, what kind of a skill set would they require to work in GW research?
So I think if you want to start professional research, there is a whole scale of progression that you have to go through, including studying basic physics in BSc, and then MSc, and so on. And there's a rigorous training in graduate school that you have to go through. But one could slowly acquire some skills during the process of undergraduate education also. So apart from having a good grasp of fundamental physics, some skills in numerical calculations is very useful. In fact, it's useful in most fields of physics and astronomy now. Some understanding of statistics, which is not really commonly taught in physics courses. So the things, so the additional skill that are useful for gravitational astronomy would be some skills in numerics, statistical data analysis, and etc. And popular understanding of astronomy is also very useful. This is a thing that you can do in addition to doing well in your actual classes.
Thank you, Professor Ajith. Now I'll be moving on to Zoom questions. So Zoom attendees might be thinking that the questions are not being asked. These questions were from YouTube. So Zoom questions. Devang is asking, can lensing due to galaxy cluster help us to see very distant objects which we can't see normally?
Yes, I think I told an example of that, a distant star that you would not have seen otherwise. And there are many, many examples of that in electromagnetic astronomy. The star was one of the extreme examples.
Thank you. Neil is asking, what is MACHO? Yeah.
It stands for Massive Astrophysical Compact Halo Objects. It's a very fancy acronym for compact objects that can contribute a fraction of dark matter. One example would be black holes.
Thank you. Neil has another question, which seems interesting. How do we know this star is 9 billion light years away, as an example, and not some new star formed during a supernova event?
Because we can measure its spectrum, and by looking at the redshift of its spectral lines, we can measure its cosmological redshift. And that's why you get the estimation of this 9 billion light years.
Thank you. Kaustubh Gupta is asking, is the mass of an exoplanet big enough to cause noticeable lensing?
Yeah, it seems that even a few Jupiter-sized mass is good enough to, it's something that we can measure using current technology. Of course, as I said, any masses would cause gravitational lensing. So the question is it larger than our measurement errors? And using current instruments, I think if we can see the gravitational lensing signature of a planet with a few Jupiter masses.
Thank you. He has the next question. How do we know that dark matter is more diffuse than baryonic matter?
Because it comes from various observations. One is from the observation of the rotation curves of stars in galaxies, which is a classic observation, which is almost 80 to 90 years ago. And if you want to, so if you look at the rotation velocity of stars as a function of distance from the galactic center, and you can try to fit that observed motion using a Newtonian potential. And it turns out that it has to be much more extended and diffused than the gravitational potential suggested by the luminous baryonic matter.
Thank you.
And there are similar other observations also.
I see. Thank you. So next question is by Anandu. Since dark matter is not known to interact with matter and light directly, how can we know that the lensing is caused by dark matter? And how do we differentiate between dark matter lensing and ordinary matter lensing?
Lensing doesn't care whether the matter is dark or bright. One can the lensing is contributed by the total mass of the matter, but now then you can look at that part of that galaxy or cluster, and astronomers have some ways of converting the observed flux to mass. There are some empirical relations suggesting that that helps them to convert brightness to mass. And that's why we measure the mass of galaxies and so on. But it turns out that the mass that is estimated from the luminous part of the galaxy is much smaller than the total mass inferred from the lensing. So our inference is that most of the matter is in the form of dark matter.
Okay, thank you, Professor Ajith. Next question is by Debojyoti. He's asking, unlike the optical lenses, the achromatic nature of gravitational lensing, we can get an enhanced brightness of the surface brightness of the image formed by the lens. Can, from the notion of brightness enhancement, we can use as a standard candle for finding new star and galaxies? Very longish question. Yeah, this is it.
So are you suggesting that so if you're suggesting that if you see an unusually bright star, can we infer that it is produced by lensing? I guess that is what you mean.
I'll repeat the question again, Professor Ajith. Unlike the optical lenses, the achromatic nature of gravitational lensing, we can get an enhanced brightness of the surface brightness of the image formed by the lens. Can, from the notion of brightness enhancement, can be used as a standard candle for finding new stars and galaxies. I think he's trying to compare the EM standard candle versus if we can have another in the gravitational wave regime.
I don't think he's talking about gravitational waves yet, but my understanding is that if you're asking whether if you see an unusually bright star, can you guess that it is gravitational lens? I guess, but I don't know if there is an upper limit on the brightness of stars. I guess because there is a natural mass upper limit on the stars. So there is also some brightness upper limit. So I guess that if you see an unusually bright star, that can be interpreted as an evidence of lensing.
I see. Okay. Thank you, Professor. We'll move on to the next question. Why is there a mass gap in black hole mass ranges by Jayesh Jain?
Yeah, we don't know. So it turns out that the lightest black hole that we have observed using electromagnetic waves is of the order electromagnetic observations of the order of 5-6 solar masses. And the neutron stars, we know there is a natural upper mass limit because if the neutron star is more massive, then it won't be able to balance against the gravitational force and it will collapse into a black hole. But why is there a mass gap between, say, 3? That's about 2.5 or 3, or somewhere between 2 and 3 is what most people believe. But why is there a mass gap between 3 and 5? It's not entirely clear, but some people, it might have to do with some supernova mechanism, which would cause some part of the mass to explode and leave the star, etc. But I'm not entirely sure what is actually causing this mass gap. But it is an empirical observation.
Thank you, Professor Ajith. Next question is by Ajith Ekbote. He's asking, would gravitational waves be waves or particles as the similar to dual nature of light? Can de Broglie principles be applicable to the gravitational waves?
And we don't, so if we have a quantum theory of gravity, then there will be a sort of a force carrier of gravitation, which is currently called graviton. But we don't really have a satisfactory theory of quantum gravity yet, and we are very, very, very far away from having any observational signatures of quantum gravity. So any particle effect on gravitational waves is we have no conceivable way of measuring it. So we have no analog of photoelectric effect in gravitational waves. We won't have any in the conceivable future.
Thank you, Professor Ajith. Next question is by Raghav. What kinds of information provide us about the universe? As I heard many times, the gravitational wave is opening a new window to the universe. So I think general question about gravitational waves, what kind of new information does it provide?
Yeah, so you already saw some examples. We saw that the black holes in the universe could be much more massive than we thought earlier. There are objects that are inhabiting what is called a traditional mass gap of between neutron stars and black holes. And we have got some interesting hints of the state of very dense nuclear matter that exists in neutron stars through observation of gravitational waves from binary neutron star system, which would improve in the upcoming years. We have done some very interesting tests of Einstein's theory in the regime of extreme velocities and extreme gravitational fields. And this is the first time Einstein's theory is tested in these extreme regimes, which is one of the theory is one of our fundamental building blocks or pillars of modern physics. We have started using gravitational observations as a way of probing the cosmic expansion rate. These are in the very beginning stages, but they offer a new way of measuring the cosmic expansion rate. And also, these can be, now, for example, we now understand what is the engine that powers these, what is called the very, very luminous phenomenon called the gamma ray burst, the short gamma ray burst. Because we observed a merger of two neutron stars in coincidence with a short gamma ray burst in 2017. So there are already several such new information that we learned through the observation of gravitational waves. And in the future, there will be many more. And the most sort of ultimate example would be observing the gravitational waves from the very, very early universe. And this is something that is it's a unique thing that gravitational waves will be able to do, because currently the earliest light that we can probe from the universe is the cosmic microwave background radiation, which was generated some 300,000 years after the Big Bang. But now, if you are able to observe the gravitational waves from the early universe, we will be able to understand the physical situation of the early universe, even a fraction of a second after the Big Bang. So these are some examples of what gravitational observations could have done so far, will do in the next few years, and can do in the next several decades.
Thank you, Professor Ajith. So it's already 5 past 6. Are you willing to take more questions? We have like another 10 questions.
Maybe you can take 2 more and then we can stop.
Sure. Sushmita is asking, why is there a magnification of light from background quasar? Is the total flux increasing?
Well, total flux of all the images will be conserved. So if it means that one image is magnified, we would have some demagnified image of the others.
Thank you. Preeti Gupta is asking, if we have an EM counterpart with the GW signal, can lensing bias the constraints on the speed of the GWs?
Can lensing bias the constraints? I don't think lensing would bias the constraint, because both gravitational waves and light would be lensed in the same way. And in fact, they would provide some very interesting additional measurements. So there are some papers already discussing what kind of interesting cosmological measurements one could do if you observe a lensed gravitational wave signal as well as a lensed electromagnetic wave, such as a lensed GRV.
Thank you. I think we'll end the Q&A with this last question by Ajith. Even I would like to know about this. So can artificial intelligence be used or is being used to study and predict gravitational lensing and gravitational waves?
Yeah, there are machine learning tools being employed in the study of gravitational lensing. And one such citizen science, so for example, one interesting challenge is if you have data from some large cosmological surveys identifying, for example, strongly lensed galaxies in that large data set. And there is a very interesting project led by our colleague Anuprita More at Ayuka in collaboration with IPMU, Japan, Tokyo, etc., which I forget the name. It's a volunteer involvement project. Well, like it involves volunteers as well as a machine learning backend. So the volunteers can sign up to train the machines by helping the machines to identify the images. And eventually the hope is that the machines will be able to do that, etc. There are various ongoing work, including by some of us, to use machine learning to identify such lensing signatures in the gravitational data. But it's all in the rather early stages.
Thank you, Professor Ajith. And there's one more question. I think there's a foreign participant. I cannot pronounce his name, but the question is that are there any graduate programs straightly related to gravitational lensing?
No, I think that would be too focused, because this is one powerful tool to explore astronomy, but the essential skill that are required to study gravitational lensing involve various branches of physics, especially GR and various branches of astronomy and so on. So I think focusing too much on gravitational lensing at undergraduate level would be a bad idea.
Thank you, Professor.
Actually, I can take a couple of more. I think I see some complaint that why don't we go till the end? So I'm happy to answer more questions. How many?
Sure. So we have like another 5 or 6, because there are some repeat questions, like similar questions. So I'll continue then. Okay, thank you so much, Professor Ajith. So Ravi Singh is asking, is there any specification how much angle formed as per heavy object? Is this good way, mathematical way to find any kind of black hole? The question is not clear, so I can skip if you would like. Okay. Shahayadri Krishna is asking, by solving for the two polarizations using the method you talked about, what can you infer about the source of the GWs?
When we can measure its polarization angle, then we can check whether there are any extra polarization content in the waveform, which would be more like informing the theory, not necessarily the source so much. So for example, if you see the presence of an extra polarization mode, like what is called a breathing mode or a vector mode, etc., then that would be a definite violation of Einstein's theory. So it's more like a way of testing the theory than understanding the source.
Okay. Thank you. Kaushlesh Chandra is asking, can multi-universe hypothesis explained as consequence of gravitational lensing?
No.
I'll move on to the next question by T.N. Shrikant. Electromagnetic lensing conserves certain properties of the source, example, surface brightness. What properties will be conserved in a GW lensing event? Can you please comment on this?
Same, the total magnification, so the total luminosity will be conserved.
Thank you. Munib Bhatt is asking, at what gravity does a gravitational lensing become observable? I think when gravitational lensing is observable, that's the
it is a question of your measurement device also. One can answer this only in the context of a specific measurement device.
Yes.
If you have a measurement device with infinite precision, you can measure even the tiniest gravitational lens.
Thank you, Professor Ajith. He has another question. Does gravitational lensing provide time evolution information?
Yeah. I mean, if you are able to observe it in time, yes. So for example, gravitational wave observatories do measure the gravitational wave signal as a function of time. So it can, for example, then observe deformation from the unlensed waveform and so on. And astronomers also now are using the so-called time domain astronomy, which is basically not only looking at some static image, but also going back to the sky and measuring it multiple times and making some kind of a movie out of that multiple exposures. That's how, for example, they measure, they observe this evolving lensed supernova.
So it is being measured. Great. So next question is by Preeti. I think this is the second question by Preeti. Can you comment on the difference between the transit method in astronomy and microlensing, because the former shows a dip in brightness flux?
Yeah, the transit is basically just the brightness that is covered by the opaque body, right? And that is cutting some part of the power. While the lensing is basically focusing light and is enhancing the brightness. But they are in a very similar physical situation.
Thank you, Professor Ajith. This is a very interesting question. Vipul Prasad M is asking, does interference of gravitational waves cancel each other in some region of space and create blind spots?
Yeah, gravitational waves can also interfere. And for example, this sort of wave optics effects that I talked about is some manifestation of such interference, because you can think of them as having gravitational waves coming through multiple paths and interfering. And then they could have some beating patterns.
Thank you, Professor. So one question is by Saklan. He's asking, what things are you expecting from an undergrad student to know in order to get accepted for the, oh, sorry, this is the, I think we have covered all the questions, but maybe I will ask this question to you, Professor Ajith. I'll complete this question. Saklan is asking, what things are you expecting from an undergrad student in order to get accepted in summer visiting program in the field of gravitational waves at ICTS?
It's a tough question, because we get a few thousand applications, and we select on the order of 10 people in every season. So knowing something is not really sufficient to guarantee an admission. But generally what we are looking for is people who have done who have very good background in physics and some experience in numerical computation, and have done some research projects in the past, so that they have some established and shown some ability to do research, if possible, more or less with very little guidance and so on. And generally like a problem-solving attitude, people who are able to solve problems independently, etc.
Thank you, Professor Ajith. I think we have covered almost all the questions, and thank you for the wonderful talk. Thank you everyone for joining. If Professor Gopakumar is still there and he has any comments, Professor Gopakumar, you are free to tune in, but it has been long. I don't know if he's still around.
No, I think he has left.
I think he has left. Oh, thank you, Professor Ajith, for the wonderful talk. And everyone could just wait for the announcement of the next Vigyan Adda talk. This was the second talk, and a wonderful way to celebrate our National Science Day today. Thank you so much, Professor Ajith. You have any comment, please, you can.
Yeah, thank you everyone for listening, and I hope that we all celebrate the spirit of the National Science Day, and it's not only a way of celebrating science, but also we, as sort of students of science and citizens of India, we have the responsibility of spreading the scientific temper to a wider society, which is more and more needed now. So I hope that you all be torch bearers of rational thinking and scientific method and evidence-based inquiry and so on. So thank you all.